Cool. All right, let's get started. Okay, welcome to Lecture 8, Mobile Sensing, Learning, and Control. Course logistics for today. So A2 is due this Friday. The constraints are on the website, and I relaxed them a little bit. So essentially, you are trying to detect two tones. I may not have. You guys are looking at each other like, "Oh, this is great." All I did was relax what you were able to detect in two tones. They have to be at least 100 hertz apart now instead of 25 hertz apart, which makes things significantly easier. If you write an algorithm that detects two tones that are 25 hertz away from each other and it can do it pretty well, I'll give you extra credit up to a point. Okay? A point on the assignment, so like 11 out of 10, right? So a full point on the grade scale. Okay? Cool. If you're feeling lost, I have a feeling you're not alone right now based on some of the feedback that I'm getting. So what I want to do today is start with a quick FFT review and then go through some more examples of using the audio manager, right? And to basically try and show you how easy a lot of this setup is or make it easier for you. So when we get started, you'll have a better idea about it. I'm then going to go over some profiling and some debugging with Xcode so that it's maybe a little easier to go through and try and figure out what problems you're hitting and where. And then I'm hoping we'll have time to start and go into core motion, where we're actually going to be getting things from the coprocessor that handles all of the accelerometer data, gyroscope, all that kind of stuff. But if we don't get to core motion, we don't get to core motion. I think we'll get it started. Okay. So this is just a quick one-slide FFT review. And this is the high-level information from the FFT lecture that I want you to kind of remember. Like if you remember nothing else from it, or if you're completely lost in it, remember these. Your sampling rate is going to dictate, basically your sampling rate tells you the time between each sample that you're taking, right? So if you're taking, 1,000 samples per second, what's the time between each sample that you're taking if you take 1,000 per second? 1,000th of a second, right? It also tells you the max frequency that you can measure, right? It's half of your sampling rate. So if I'm sampling at 1,000 hertz and a sine wave comes along that is 200 hertz, am I going to be able to detect that? Yes, right? I'm sampling at 1,000, so I can detect any frequency up to 500 hertz. What happens if a sine wave comes along that is 700 hertz? You'll detect something. You'll think it's a lower frequency sine wave, right? Because you're not sampling fast enough to be able to detect it, right? And that was called aliasing. Okay? Everybody okay with that? Right? Like something's going to show up. It's still exciting the microphone, but you're not going to be able to tell what frequency it's at, because you're not sampling fast enough to get a 700 hertz sine wave. Okay? So your resolution and frequency, this is just essentially, when you take an FFT, you get, an array back. And each index in the array is a specific frequency that you're looking at, right? So when we talked about the FFT, if we were talking about resolution, I'm talking about, each of those bins, what frequency do they represent? Okay? So the very first index, the 0th index of the array, what was that? Anybody remember? It's the average value, right? It was like the 0 frequency, right? Frequency of 0, right? So it was the average value of the function. And then you mentioned the Nyquist rate, right? So if you look at the, kind of the very last bin on the FFT there for analysis, that's essentially your sampling rate over 2, right? And then we also talked about what each frequency bin represented, right? So each of those is a frequency, and if you want to get the frequency of each of those points in the array, what was it? It was determined by how fast you're sampling and how long the FFT is that you're taking, right? So this Fs over n tells you what the frequency resolution of each bin is, right? So for the assignment, I'm asking you to basically have an accuracy of 12 hertz, right? So what does that mean for 12 hertz accuracy? You're sampling as fast as you can, 44,100 samples per second. What size of FFT do you need to be able to have 12 hertz accuracy? Yeah. Essentially, it's, right? So, what? What am I trying to say here? Essentially, we've got that we need 12 hertz accuracy. That's equal, right? I want this to be less than or equal to this. Is that right? I want my resolution to be this. So if f of s is 44,100, what does n need to be to get 12 hertz? This is the equation that you want, right? Essentially, that's the value that you're looking for. All right? And it's somewhere around 4,000 something. I don't know exactly what it is. I can't do that in my head. I'm sure one time I could. No?
Oh, you want us to actually do it?
No, you don't have to. I'm just giving. I don't care that you can do this. You can put this in a computer. I want you to know how to set up the equation, right? You can set up the equation. You're good to go. If you can punch it into a calculator, awesome, great. I'm happy for you. The last thing that we went over, which I lost a lot of people on, was windowing and convolution. And essentially, what I want you to get out of that is there was this thing called leakage that occurred when you have a sine wave, and windowing helps essentially diminish the effects of one sine wave leaking over, its energy leaking over into all of the other frequency bins that you have. So essentially, you can try out some of the windows that we talked about last time using the FFT helper, and maybe we'll do a couple of examples to show you kind of what that does to your FFT, right, to get a better idea of what you're actually working with. Okay, sampling from the microphone, right? Let's do this really quickly. Here's what I want to do. I essentially want to take our Rolling Stones app, which I've brought up right here, and I want to convert this over to sample from the microphone. Okay? So how would I do that? Well, first of all, let's see what's going on here. All I've done right now is rearrange this from last lecture so that the functions are in a slightly better manner. All right, so essentially I've got That's not really going to show up very well. Okay, we'll just scroll down here. So I've imported all of these controllers and all these classes. I've got a K buffer length of 4096. Okay? So I've got an audio manager, a file reader, a buffer where I hold samples, and then I'm graphing all of that and saving it into audio data, right? I also have this thing called FFT helper and the FFT magnitude buffer. So just to remind you of what we did last time, the only thing that we did was inside view did load, I allocated my audio manager right here, and I set up this ring buffer to be of length K buffer length. Okay? The FFT helper, all I did was allocate it, and I said that I want to take an FFT that is K buffer length. And then I set up the graph right here. Now, here is where all of the audio stuff is happening inside of the Play Rolling Stones, right? So essentially, I've got this file reader, right? So this is a file reader right here. I'm allocating it, and I'm pointing it to the file, the Rolling Stones file. So what happens here inside of my set output block is that this audio manager is already running. And this output block is taking this array right here of data, and it's setting it to the data from the file, right? So I've got my file reader. I call this function called refresh or retrieve fresh audio. So it goes out to the file. It grabs audio samples. How many audio samples does this grab, this function? Num frames, right? Num frames is the number of samples that I need to grab, right? It's also the length of data right here, okay? So all I'm really doing here is grabbing those, and then I'm setting them to data right here.
And what is num frames? Where do you define the size?
Num frames is passed in. These are all input arguments right here to my block, right? So when this block exists, it has data. Whatever I put into that array is going to get played out to the speakers, okay? Because I'm in an output block. So whatever I set into there, if it's a sine wave, hint, hint, a sine wave will be played out to the speakers. If it is samples from a file, which is the Rolling Stones is going to get played out to the speakers. That's all that this block does. It grabs the raw time samples that make a song and just plays them out to the speakers. And it's continually grabbing fresh samples.
The song is the one that will have the number of frames and all of the array set up. Like, it will take it from there.
Mm-hmm. Mm-hmm.
And then for the FFT we're reading, it's 4096.
Yep. Yeah.
So
the number of indices in the array is 4096. Because that's array. So where that comes from is I've got this buffer, and in addition to taking that data and playing it out to the speakers, I'm also saving it into this buffer, right? So I'm reading those samples from the file, I'm saving them into the buffer, and that allows me to go and grab those samples on my update function. My update function comes from OpenGL, right? And it's running at 15 frames per second or 30 frames per second, wherever we set it to be, right? And so every 15th of a second, this function gets called. It's like, oh, okay, let me go get some audio data from that buffer that I was saving from. Let me just put it on the screen, right? I'm going to set it into the graph. I'll plot that. Then I'm going to take that audio data and take the FFT of it. So it takes the Rolling Stones, takes the FFT of it, and then graphs the FFT, right? So if I were to just run this, right? This is what I get, right? I set the audio samples. That's what it looks like. That's just the raw audio grabbed from the file. If I were to take the file and plot it, that's what the Rolling Stones look like. If I take the frequency of it, it looks like this. It doesn't make a whole lot of sense, right? This is a bunch of instruments and drum beats and all that stuff. It's the frequency content of all of that drum beat. Okay? All right, so I'm going to stop that. What if I want to take that and I don't know. What if instead of writing to the output, what if I want to grab microphone data? How do I do that? Set input block. Okay, I'm not going to write out to the speakers anymore. I don't care what the speakers are doing. Now I want input data. So this function set input block, I've essentially data right now, when it comes in, it doesn't need me to write anything into data. Those are samples from the microphone. And the length of data is num frames. So let's say num frames is equal to 1,000. I have 1,000 samples that it just read from the microphone that I have access to, that I can do stuff with. Okay? So instead of, all of this file reader stuff, let me just get rid of this. Let me just comment all of this file reader out. I just commented all of that out. What's going to happen now? Well, I've got this data from the microphone. I'm saving it into my buffer right now, right? That's what we were doing before, except now I'm taking the microphone data and saving it into the buffer. Is that okay? Yeah.
So in this case, you have to save it to the buffer, or would you just have access to the data using the set input block?
You do have access to the data from the set input block, but that set input block, when we very first started talking about audio sessions, it was like you had to basically make a callback function that says, hey, whenever audio is ready, what are you going to do with it? This is that function. This is a block. So this is basically your callback function. So whatever you do in here, you need to do really, really fast. Because if you take too much time, it's going to have more audio samples ready. And if this block isn't finished executing, it's going to drop those samples. You know what I mean? Right? Because it's just filling up a buffer with audio samples. And if your code hasn't finished running, it's going to drop that frame. You're not going to be able to process it. Okay? So to get around that, we just copy it. Say, hey, all I'm going to do in this block, I'm going to copy it. I'll do some processing later with basically my little OpenGL update function, right? That's running at 15 frames a second.
It's sort of unrelated, but why did you put it in view will appear and not in view did load or update? Like, how would you choose where to fit it?
You can. I put it in view will appear, and the only reason I did that is so that everything is kind of set up before I start adding audio blocks onto the queue.
Does that mean like when you?
It's the very last function inside of your model view controller lifecycle before things just start displaying the screen.
So view did load happens before that.
View did load happens before view will appear in the lifecycle. Right? So I'm just waiting to the very last minute to start this because essentially once I set this input block, that it's going to start processing audio data, even if nobody can see it yet. Okay, you can do that in view did load. Yeah, yeah. I think it's matter style. It doesn't matter too much. Yeah. So will this work? Am I sample? What is my code going to do now? It's going to keep filling up this ring buffer. And whenever that ring buffer is full, it's just going to start overwriting data in the ring buffer, right? It's just this ring buffer, right? So I'm going to get 4,096 contiguous samples in this ring buffer. And I'm already taking the FFT of it. Because that's what I was doing with the output block before. So let's see what this looks like. I can just run this now. You see it? Right? So it's a sine wave, right? That's the frequency content of me talking, by the way. You'll notice that everything is approximately below 6 kilohertz, which we talked about before. There's a lot of low frequency content, but unless I start talking, unless we have like a child here that starts talking in a really high pitched voice, you're not going to see much frequency content above there. Okay? A little bit better on how to use the audio manager. It makes things really, really easy to get access to the samples. Otherwise, it's just a headache, right? Okay. All right, let's stop that from running. There I am. Okay, let's put that up here. Okay. Wow, that is way too big. Hold on. Making a sine wave. Okay. So now I want to take a sine wave and set it to the output. Okay? How would I do that? Well, this is the equation for a sine wave, right? So if I want g of t to be the samples of a sine wave, the equation for that is sine of 2 pi ft, okay? Where f here is the frequency of the sine wave in hertz, t is time in seconds, right? This is just, it's a sine wave, right? So t goes from 0 to 1 second. I could put it in there. If I want to play this out to my microphone, what's the problem here? I don't have t, right? Does that make sense? We're working digitally. We have an index that we need to save it in an array, right? I have an index that's from 0 to num frames, right? So 0, 1, 2, 3, et cetera, all the way up to the number of samples of my data array. I don't have time. Well, how do I get time? You guys know. How do I get time?
Sampling rate.
The sampling rate, right? So that's a continuous sine wave. A sine wave from samples looks like that, right? So if my index goes from 0 all the way to, however long this is, in time, how do I represent what time is here, right? What does t equal? It's one over my sampling rate, right? Right? So it would be this, 0 over f sub s, 2, 1 over f sub s, all the way through. That's what time is equal to, right? So the equation for this sine wave, so g of n here, where n I've given it these square brackets, right? So n is now an integer that I'm putting into it. It's sine of 2 pi s, n over my sampling frequency, right? What is f in this equation? What's f? The f right there. What is that?
Frequency.
It's the frequency. It's whatever you want it to be. It's a constant. 100 hertz, if you want a 100 hertz sine wave. Okay? So how would I code this thing up? How do I program that function right there?
Math library.
In the math library. Yes, actually, yeah, absolutely. Right? So data is g right here, right? So from n equals 0 to num frames, and then I'm going to add some to it, n plus n, whatever you want to do. And then it's sine of 2 pi times my frequency that I want, times n, divided by my sampling rate. Right? Easy as that. Wonderful. Don't do this in your homework. You'll get dinged. Why? This is not inefficient. This is not efficient. Why? Why is this not efficient?
You have to calculate the sine of everything in real time.
Yeah. Yeah. What would make this more efficient?
You save it first as an array and then you just play it again. You do the equation once.
You could do that. If you do that, I'm going to love that. What's another way of making this slightly more efficient?
Do the sine of 2 pi. So essentially it's 1, where the n is 1, and then just add then just keep adding that number each time.
This?
Yes.
Okay, so essentially,
In short.
what I'm doing here is instead of multiplying 2 times pi times frequency divided by sampling rate every single time, the only thing that's changing in there is n, right? I'm doing all of these different multiplications that I don't need to be doing. So I do all the multiplication once at first, so I've got 2 pi frequency over sampling rate, and data at the end is equal to sine of phase. And every time I go through this, I add into phase that increment. Is that okay? Will this work? No, I get some people shaking their heads because they went through it.
You only play once. I mean, that's not a thing you need to repeat.
Yeah, it needs to repeat itself, right? So what do I do? What's a possible solution? An infinite loop. Essentially, right, I've got these blocks of data that come in. I kind of want to like save state of where I am inside the block, right? Because I've got, let's say I've got 1,000 samples that come in. I want to create a sine wave, put it out to the speakers. I'm going to get another 1,000 samples from my audio manager, and then I'm going to keep doing that. I'm just going to real time, keep chunking it in. All right, so what if I did something like this, where I said, okay, my frequency that I want, 18 kilohertz, right? Nobody can hear it, right? Which is good, especially during lab time. All right? I'm going to have a block float called phase. Yeah.
I just wanted to say, like when we were running that the second part, what we noticed is whenever the phase is like, say 18.5 or 18.5 multiplied by 1,000, you would actually hear it. But on like 15, 17, or 16, 17, 18, 19, or 20, you couldn't hear it. But in between, you hear the sound.
You're talking about the frequency?
Yeah. Like when we use a slider to set, you know how the slider is in range, like it's 17.5. Then we multiply it by 1,000, so you get like 17,500. You would actually hear a sound, but then when it's like on 17, on 18, on 9, or close to, you couldn't hear anything. I thought that was interesting.
That is interesting, and I know why, and it's not apparently obvious. Okay? So essentially, let me just take the code that I had from the previous slide and insert it onto this set output block, right? So essentially, I've got my frequency, phase, and sampling rate, right? What does that underscore underscore block command do?
Sets it for the next block.
Yeah. If I can set phase and sampling rate outside of the block without the underscore underscore block command, it's just I cannot change the value of the variables phase and sampling rate while I'm inside the block unless I put that up there. Okay?
So the underscore is an actual function.
Underscore underscore block. It tells the compiler that essentially these variables, I want them to be able to be manipulated inside the block. Okay?
So they're not constant.
Not if I put the underscore underscore block. There's a little more processing that has to happen so that I can kind of look at locking with that variable, but it takes care of it for me.
Why did you just put it then inside?
Declare them inside? Well, the only reason sampling rate is actually something from the audio manager right here, right? So audio manager dot sampling rate tells me the sampling rate that it's set up, right? So this is my little Novocaine audio manager dot sampling rate. So I save it outside of here. Okay, so I have this phase increment, which is 2 pi f over the sampling rate. I have I that goes from 0 to frames. Data at the I is equal to sine of phase. Phase plus equals phase increment. Is this essentially kind of what you guys did? Right? You heard some artifacts, right? Why? Yeah. Essentially, so a sine wave looks like this, right? Time goes from 0 to whatever the period of my sampling rate is, or the period of my sine wave is, right? When time goes past that, what needs to happen? I need to kind of shift it back, right? The sine wave is repeating, so I need to shift it back. What do I need to shift it back to? Did you guys shift it back to 0?
We tried.
1 minus. You subtract its period.
You subtract its period. What is a sine wave periodic about? Anybody know? Anybody remember? What's the period of a sine wave? 1 over the frequency. What if the frequency is 1? Then time goes from 0 to 2 pi. Right? Right? This is like going back. You guys are going back to high school with this. You're like, what was it? Yeah. It's fine. I know you don't remember. So my sine wave repeat max is going to be 2 pi, right? So whenever phase is greater than or equal to sine wave repeat max, I want to subtract that off. This will protect you against some of the things that you guys, I think the artifacts, right? This will protect you against like when you're trying to make a frequency that is not an integer of your sampling rate. Because you don't really have to do this when the sine wave is an integer of your sampling rate because you're always going to be taking it back to 0. But essentially what you want to do is subtract off a period and then keep going. Yeah.
Does the audio manager already set the sound to be in hertz, or is it in like megahertz? Like how do you know that the phone is actually playing those hertz and not just a number that you gave it?
Yeah, okay, I can see why you're skeptical. But essentially, the set output block is setting up parameters into the audio card of your phone, right? That audio card will run, like you tell the audio card, I want you running at 44,100 samples. And I want you to play out to the speaker at 44,100 samples per second. And you rely on me to hand off data to you fast enough so that you can play it continuously. And it's going to do it. It will do it.
And the card plays in hertz?
All the card understands is that I need to play out at a certain hertz. So it understands hertz from that. And all I'm going to be giving it, I'm going to assume that all of the data that you give me is at that sampling rate so that I can play it out as fast as possible. And so essentially inside of this num frames right here, so this is set output block, this is how many frames it's requesting, right? It's saying, okay, I'm going to play out another block. Give me 4,000 samples. So I'm going to give you 4,000 samples, play those out, right? And as, you know, it takes time to play those out, and it's going to call this function again and get more samples from you. And it will work. It was designed to work, right? Should we do this? Let's do this. Here's what I'm going to do. I'm going to take this code that we had here. Oh, you know what? I think I made this. Whoop. Let's go ahead and go in here and set it up. Here, let me get rid of all this noise. I'm going to set up an output block with my audio manager. It's going to look like this. Frequency is equal to, you know what, let's just make that a block float. Okay? I'm going to go in here. What did I have here? Whoops. Wow. And then what?
The whole max value
Equals what? M pi. 2 times pi, right? And then if this phase value is ever greater than the repeat max, then I don't want to add it on there? No, you're right. I'm too used to plus equals. Anyway, yeah, so I'm going to subtract that off. Will this work?
in theory.
In theory, it's going to work. You don't think it'll work? I think it'll work. All right, so I'm going to play it at 18 kilohertz. Actually, I'm not. The reason that I'm not is because if someone is listening to this lecture, the sampling rate of my computer is not 44.1 right now. What's happening is this is going to alias back down, and you're going to be listening to this, and the second that I play this, it's going to sound like when you're listening to it, it's going to wash everything out. So I'm going to actually make it an audible tone, okay, so we can all hear it. Okay, so let's do 600 hertz. Does anybody know what middle C is? No? Shall we Google it?
Oh, wait.
Oh, come on, you got like...
Oh, 261.
261?
Yeah, I just typed in middle C and Google was like...
Google's like, oh, 261 hertz.
That was 261 hertz.
Okay, so 261 hertz. So I'm going to play middle C on the phone. All right? Google was happy enough to do that for us. Okay, so phase, sampling rate, they're all set up. Let's play this to the phone. What's going on?
I think it's actually higher.
I mean, I just did what Google said. No, yeah, 261 should sound like this.
I agree. I agree. What's going on?
Is there like,
Is it hearing itself?
oh yeah, it's hearing from the microphone.
Yeah, but I'm not playing out from the microphone, right?
Oh, you're
Data from
All right, hold on.
formula.
oh no, never mind. Oh yeah.
Essentially what I think is coming on here is num channels is equal to 2. But that's only true on my laptop, not because it's through AirPlay. I should have done an AirPlay demo with this before so I could solve this in real time. It also might be that I need to make this. I don't know if it's clipping. I don't think that it's clipping, but let's just check it and make sure. Okay. Well, yeah, it did get lower. Let me see if I can just actually put this in here for... Essentially, what needs to happen here is this needs to be for int j equals 0, j less than num channels. And then plus... That's going to be, whoops. So when we do the channels, each of those channels, they're interleaved, right? So it's like left, right, left, right, left, right, right? I want to play that out to each channel. Does that make sense? This data array, it's going to take every other sample and put that on the left speaker. It's going to take every other sample and put that on the right speaker. Okay, so if I do this, what should this equation be? Whoops. Is that right? I want to take I, right? So the number of frames that is coming in, there's one frame for the number of samples that it needs, right? So it's like, okay, give me 1,000 samples for each channel, right? So the data array would be 2,000 long. And I'm just setting every other sample to be this sine wave. Okay? There's more efficient ways of doing this, but that's fine. We'll do this. You think this will work? I don't know. Let's find out. Can you guys hear that? And I've got a nice little sine wave with my voice as well. Is that okay? Okay, let's turn this off for people that are actually watching the video of this lecture. All right? Good? Happiness? We're all kind of happy with the audio manager now. Got some stuff going on. All right. Let's go back to here. All right. What's next? Feeling good. Profiling. Let's go back to Xcode here. Okay, so let's do some profiling. I want to know maybe how efficient this is. I want to know how much memory I'm using. And Xcode has an integration with iOS that is incredible, right? Why? Because the people that write Xcode have access to the kernel of every single machine that they build, because they build all of their iPhones, they build all of their Macs, right? So if you want to look at profiling, it is completely built in to your debugger, right? Which is Xcode, right? Does that make sense? It can help you find memory leaks, right? So let's start making some changes to my thing that I've got right here. I'm going to go ahead and take out this output block. I don't want to play anything for people that are watching this lecture. So I'm going to stop playing the sine wave. I'll leave the code in there and post this after lecture. Okay? But essentially, let's go out to our view controller and say, hey, I don't want to just start on this, this OpenGL view controller that we set up. It's just, playing a bunch of stuff. I actually want to start from a table view. Right? So I'm doing my homework. I'm feeling really good about myself. I'm going to put this inside of a navigation controller. Right? So we're going to do this. Is everybody with me on this so far? Yeah. All right. The initial view controller, I'm going to start here. And then let's go into my table view. I'm not going to subclass it. I'm just going to make some static cells and point them. Right? So move this up here. Okay, so here's my table view controller. Here's my table view. Everybody know I double-clicked into the table view. We're all fine with that right now, right? So there's the view controller and then the view. Good. Okay, so essentially what I've got right here is I want these to be static cells. One section, we'll leave it as 3 cells, that's fine, right? This first cell, I'm going to make just a basic. And the title of it is going to be Listen to Microphone. Okay? What's the next thing I need to do? Because I want this to go to that view controller. What do I need to do? Somebody tell me. Anybody? Control click. I want to do push, right? Push. Awesome. Feeling really good about myself. Okay, so now, if I were to play this, right, it should just work. Here it is. Listen to microphone. Listen to mic. Oh. Sorry. All right, so I'm listening to the microphone, right? I'm good. Now I'll just go back here. I'll go forward. Oh, I can't interact with it anymore. What's going on? Oh no. Segfault. No, well, not segfault. Runtime error. All right. What's going on? What's this thing? What does it tell me? Error for object, blah, blah, blah. Pointer being freed was not allocated. Set a breakpoint in malloc error break. What's going on here? There's a problem with the code that I gave you. What is this? What's going on? This right here, I'm trying to free memory using delete, and it's already been freed. Okay? Does that make sense? I've got this graphs thing right here, and it's trying to, it says basically error for object, pointer being freed, was not allocated. It's already been freed. Right? Why would that happen? Let's go back over to our code here. View controller. Let's see. Okay, here's my deallocation. Graph helper, tear down GL, right? In tear down GL, that's where it does all my deallocation stuff. And view did disappear, I'm also doing a tear down GL. Right? So I would say this is a fault of the class. If you try to deallocate it multiple times, that should be okay. Right? Like, as a safe programmer, you should be able to deallocate as many times as you want and not have it throw a runtime error. So let's fix this. Right? So basically, let's go over back to this graph helper. and let's create some stuff that's going on here. Whenever I delete something, what's the next thing I should do? If I delete or free memory, what is the first thing you should do?
Should you first check if there's something to delete,
I should check to see if there's something to delete.
and then delete if there is?
If I'm a C++, I'm writing code, and I free memory that's being pointed to by a pointer, what is the next thing I do to that pointer? Set that pointer to null. I do not want it to point into the heap anymore. Right? So I'm going to set it to nil. Okay? What do I want to do right here?
Check and see if there now.
If graphs does not equal nil. I could also just say if not graphs. This is, I think, maybe a little more obvious. Okay? What I'm going to do right up here, I'm going to move VBO and color because they're used up here. Essentially, these are some things that I wouldn't expect you to know, but see, if VBO does not equal nil and color does not equal nil, then do this. Thank you. All right, we'll clean it up just a little bit here. All right, is this going to work? It should. We hope so. All right, so now let's do this. So what's going on here? I'll go over to here. Okay, listen to Mike. I come back over. I'm talking. I go back. Hey, I can still interact with it. This is really, really cool. Awesome. The code is fixed. No, the code runs. It is not fixed. All right, so I keep wanting to click on this, but that's not the, it's not the simulator. It's my phone. Okay, so I can go back and forth, right? So let's say I come in here, and I want to look at both of these at the same time, right? So essentially, so you guys can see what I'm doing here. I've got this little thing over here, which is kind of my, it's like a little mini profiler, right? I can get a bird's eye view of the CPU and the memory usage of the app. The memory usage right now, if I click on this, it's 7.2 megabytes. Awesome, right? So let me click on this, okay? Let me go back. It's 8.1 megabytes. Okay, I'll just click on this, and I'll go back. I'll just click on this, I'll go back. Let's say I get, my son gets my phone. He starts playing with my application. He starts doing some stuff with it, right? What's going on here? What is this? Memory leak. How do I solve a memory leak? For anyone watching the video, he said restart your phone. It's a Mac. It's not Windows, all right? So that's a joke. Okay, so what do I want to do? Well, I want to figure out where that memory leak is. So I'm gonna click on here. I'm on memory. I'm gonna say profile in instruments. Instruments is something that you can use. It's an attachment that goes along with Xcode. So right here, profile in instruments, and I'm gonna say transfer over to instruments. Instruments is just a special thing in Xcode. All right, so it's transferring over the application. If you look at this now, it's no longer running from Xcode. Xcode can't stop it or start it anymore. It is still running on my phone, right? I can still go over listening to Mike. I can still go back. But I've got this little instruments panel that's right here. Allocations. Look, it's going to tell me every single malloc and alloc that I called for. What if I go over here to leaks? Listen to Mike. Back. Listen to Mike. Back. Listen to Mike. Back. Well, what's going on here? I've got a number of leaks here that are occurring. So essentially what this is I can trace all of the leaks that are occurring in my application. Okay, so if I go to listen to mic, I go back, which one, I'm trying to see which one counts up here. This one, yeah. So like a preferences to make this bigger. Essentially what's going on here is the responsible library is play Rolling Stones. So when I click on this memory leak, it's telling me where this actually happened. It's giving me the entire stack trace of where that memory was not freed properly, right? So essentially, let me double click on this. Whoop, don't want to do that. Essentially, I'm trying to get this to come up with the actual function where this is occurring. Before I transferred it over to instruments, it wasn't really in like a debug manner. So I've got all of these different things. Come on. Well, let's see what's going on. Let's go back to my code and see if I can figure out where this memory leak is occurring. And then we'll come back to instruments and see if we fixed it. Okay? Is there anything that I am allocating inside of here that I am not freeing? Well, let's go see. Let's go inside my dalloc. The only thing that I need to free are things that I call with new, malloc, or calloc. Okay? That's my responsibility. Automatic reference counting gets everything else. What?
The ring buffer.
Man, yes! You guys are right on top of this. Okay, so essentially, I've got this ring buffer. I never called delete ring buffer, right? So I'm going to put delete ring buffer in here. Delete ring buffer, bam. Now it should all work, right? All right, so it's all going to work now. Sweet. Let's have this thing work. Okay, listen to mic. Good, everything's working. Yeah, back. All right, yeah, oh. What happened? I can't interact with it anymore. I got a runtime error. I deleted ring buffer on my dalloc. Why would I get an error? What's going on here? It's trying to access this thing called mdata inside of Novocaine over here, or inside of the ring buffer. It's trying to access it. Who's trying to access it? I just deallocated it.
When you're trying to
My input block. Why is my input block trying to access ring buffer? Because it's a block of code. I'm putting it on the queue. When I put a block of code on the queue, it gets run, right? So what's happening is I click this, view, I click go back, and it deallocates everything, and it goes back really, really quickly, but I've still got audio on my queue that is about to be processed, right? It didn't stop running. Does that make sense? Right? So my queue comes along and it gets deallocated memory that it tries to access and take an FFT of, or not take an FFT of, but it tries to save more data into a ring buffer, and it's already been deallocated. So how do I solve that?
get everything that you need.
Good coding practice. I deleted it. I set it to nil. What do I?
Leave the other one take, like the insertion of the executed.
What?
Isn't that still gonna leave a leak?
A leak?
The block that was in the queue. Are you just like not
Well,
able to-
the block will get deallocated. But essentially what I need to do inside that block is not access ring buffer if it's been deallocated. Like when I put something on the queue, it is going to get run. Okay? It is not good coding practice to put something on the queue and then go, oh, and then take it off. All right? iOS really doesn't want you to do that. There's a lot of things that have to happen. You're messing with the operations, right? So instead, you just make the block self-aware, right? So what I want to do here is I want to say if ring buffer, let's we'll go ahead, not equal to nil. Then run this. Is it going to work now? It is going to work now. He says to me, play. Let's see if that's right. Okay, so I'm still good here. I've got stuff coming in back. Hey, all right. It's good. It's good. I fixed all my problems. Listen to Mike, back. Listen to Mike, back. Let's click on that memory and see it just stay the same. Let's see it stay the same. Oh, no. It's not staying the same. What's going on? I don't know. Let's look at it in instruments. Transfer. I want to look at the leaks. Let's see what's going on here. Okay, listen to Mike. Oh, I do have leaks. I've still got leaks. Where are these leaks occurring? I've got 80 bytes that aren't getting deallocated. So if I click on, I've got 80 bytes inside of Play Rolling Stones. I'm going to click this little thing up here to give me the stack trace. Let's see what this is. Whoa. No stack trace available. Those are leaks that essentially occurred before I transferred this session over. Just going to keep going back and forth here. It's two. I've got a memory leak in more than one location. I know where they are, but I really wanted to use this to show you how you can find them in the code. I don't know why it's not working there. Maybe it's because it's on AirPlay, and it's not able to find the location of where these are actually occurring. Ah, come on. Oh, do I really? Oh, look at that. Okay, let's just do this. Let's close this down. I'm going to close this down, and we're just going to retransfer. Okay, so here's what I'm going to do. I'm going to play. Go over to memory. First thing I'm going to do is go into instruments. Transfer it over. Okay. Listen to Mike. Back. Back. Something going on here. Okay, fine. Normally on the stack trace over here, you'll be able to find the piece of code where it's actually not, like, it'll show you where that memory is being allocated that never gets deallocated. Okay? I don't know why it's not working right now. It'll have a bolded thing over here that you can click on and double click and take you into the code to show you where that's happening. Essentially what's going on in here is there's a piece of code inside of the ring buffer. So if I just go into the allocation of ring buffer, so here's ring buffer, it's a class, right? Here's where it gets instantiated, here's where it gets deleted, all right? So essentially what that would have come back with is M data right here is not getting deallocated inside of ring buffer. And essentially what M data is it's getting called, but it's a float star star. It's a pointer to an array of pointers. Okay? Which is not necessarily a bad coding thing, right? Essentially you need this sometimes. However, when I deallocate ring buffer, what happens? I deallocate everything that array points to. What do I not deallocate? the array. I didn't write ring buffer code, by the way. This is from Apple. So that's not getting deallocated. Good, we found it. We're really happy with ourselves. We do. We have another memory leak. That other memory leak comes across from this graph helper. So if I look at my graph helper code, essentially what I'm going to find here is that let's just do that instead. Essentially what I'm going to find here is that I've got this thing called bounds, which I need to set equal to nil, and I need to say if bounds does not equal nil, then delete it. Okay, so now, where's my instruments panel? Let's close this thing down. Save, play. I'm going to go over here, profile and instruments, transfer. Well, let's see what happens. Listen to microphone, back. So those are my allocations. Do I have any leaks? Did we find them all? What's going on here? I really wish this was working because now I don't remember where this one is. Oh, there's something else that I'm losing. It's inside of Play Rolling Stones. I'm losing 80 bytes every single time I go back and forth here.
Is it the copy of the buffer?
Oh, let's find out. What do you mean? Where?
Like, where you copy from the file to no, in view will oh,
So I have an audio manager, I have a ring buffer, audio data, FFT helper, magnitude and phase buffer. In my dealloc, I have an audio to magnitude, phase. I should set these to nil. Graph helper, tear down GL. I don't see it. Here, what I'm going to do is take this thing off of, because I really want this to work. Let's just close this down. No, I don't want to save it. So I'm going to tell you what I'm doing with the phone rather than have it be over AirPlay. Okay, so it's running. Profile and instruments, transfer. Listen to mic. Back. There. UI application main operator view did load F required. Controller. What is it?
Is the reason we can't see it because it's inside the navigation controller and that's or the table view controller? I mean the navigation view. If we just went straight into the graph view, maybe it would work with the stack thing, like from the storyboard.
Maybe. What if I tried this? Come on.
No, we're actually looking for it.
Now we really are looking for a leak. Okay, so rather than, we've got 15 minutes left of class, let's keep going through the slides, and I will try and figure out why this is not working rather than during lecture, and get back to you guys on it. But I do think this is some pretty good debugging that we went through right here. Good? All right, so we'll figure that out.
So when you put the down arrow for the mirror leaks, is that saying that there were like, I guess, for instance, if you drop down four, it was 4 instances of error with 8?
It was me clicking back and forth. Every time I click back and forth, there's another leak.
Okay.
Right, so every time that I've allocated and deallocated, there's another leak that occurs. Oh. Okay.
Oh, did you use delete brackets with green buffer? Or just delete? Is that like okay? Oh, I don't know.
Oh, Joe. No. Well, seriously? Oh, come on. Fine. You're not going to get a picture of me for the last 10 minutes of the lecture. Okay. So the next thing that we're going to get into is core motion. And there's not going to be any more examples, but we'll go through some stuff. And I think it's going to be really cool. We do. This is an application called Moves. Has anybody ever used this app before? It's on Android too. Essentially, it's an app that tells you the number of steps that you've taken today. It tells you, hey, you've done 39 minutes cycling and you ran for 0.3 miles, right? It's a health application, a little fitness application. And it's got this little thing. It's like, hey, new in the iPhone, version 2.5, we've added all of these activities that you can do easily. So essentially, it can break down, when you were walking, where you walked to, how long you were walking, or if you were running or cycling in between there. It's kind of a really cool little app that allows you to go in and take your location and tell you how many steps you've taken, and it's kind of nice, especially if you're calorie counting, right? Pretty cool. It also allows you to do, in this new version, it says, hey, you've been training at the gym for 1 hour and 25 minutes, or you've been running and you burned 879 calories, or 32,603 steps. That cannot be in a day. Okay, week of 17th June, right? So that's really, really cool. These are some high-level activities. It knows that you spent 30 minutes swimming. How does it know that? You manually enter it into the application. It will tell you automatically when you've been running, cycling, or driving your car. Okay, which is pretty cool until you find out how you guys can use that, and you're going to think it's not very cool anymore. This thing is called the M7 coprocessor. It comes along on starting with the iPhone 5S. You will see something like this in every single phone in the next probably 2 years. Every smartphone that's built is going to have a chip like this in it. It's a 150 megahertz processor that reads all of the motion data from all of the motion sensors on the phone, right? So the motion sensors on the phone are accelerometers, magnetometers, and a gyroscope. They all feed into this chip, and it analyzes them. And if you're on the main CPU of the phone and you want access to any of this, you have to query the M7 coprocessor. Okay? So what does that mean? That means you get a lot longer battery life because this processor is an extremely low-power chip. It is optimized, and it's only running at 150 megahertz. It's not running at the full CPU cycles that this chip is doing. And the only thing that it has to do is sample accelerometer data that's coming in. So this is a true example of parallel processing, right? It is a completely separate processor that is running. The phone can be asleep, and this processor is running. Okay? And so it doesn't affect battery life at all, actually. It also gives you this really kind of interesting thing for sensor fusion where you can get more accurate analysis. This is very, very cool. So essentially, more accurate analysis means that you have high-level streams that you have access to. So it's not just the raw data. It's not that you just want accelerometer data. The M7 is also doing processing on top of all of that data to enable you to have high-level queries that you can do. You can register your app to receive updates anytime that the user switches activities or takes a step. It will notify you. So it'll tell you the number of steps that a person has taken, and it will save the number of steps that a person has taken for a week, so that you can go and ask it, hey, what was this during this time frame? It'll also going to do some activity for you, such as running, walking, sitting still, or driving in a car, or it's going to tell you whether it doesn't know. You get this for free. It does this for you. What kind of time are we looking at? Whoa, seriously? Come on. Whatever. Oh, nice. Great. That's wonderful. That is just... Here. Technical difficulties. Sorry, everybody. Okay. Okay. So if you want to get activity from the M7 chip, you're going to use something called the Core Motion Framework. And this has been around on iOS for quite a while, but now that Core Motion Framework integrates completely with the M7 processor. The overhead that you have from accessing the M7 versus, say, iOS 5, when you were just kind of like grabbing accelerometer data, is zero. It's the exact same functions, the exact same API. It handles everything for you in the background. So the way that you're going to grab activity is you're going to essentially instantiate this class called CM Activity Manager. And it's going to tell you a couple of things. It's going to tell you whether or not you're on a device that's capable of sensing activity, right? So, if you're on an iPhone 4 or an iPhone 5 instead of the 5S, you can query, say, hey, is activity even available? If no, it's like, okay, I'll just shut down that part of my app, right? If it is, maybe I'll do something with it. You're going to be able to query the past activities of someone. So you may not have known this. When an iPhone app asks you, hey, can I have access to your location? And you say yes, it has access to your activities that you have done for the past 7 days. Okay? I don't know if you consider that private data, but it can query it. Question?
So if you already took your steps, even though we might not have any app that needs that?
Yes. The M7 processor has if you're carrying around an iPhone, it has the number of steps you've taken, an estimate, right? It's not going to be perfectly accurate. An estimate for the past 7 days. Okay? It is there. You can query it. The interaction with the M7 processor and using the Core Motion Framework, it's built completely on blocks and handlers and queues. Same way that we've just used the audio manager out of the Novocaine framework. It's the exact same type of thing. So essentially, if you want to subscribe to different activities, you're going to do it through notifications. So here's what the code would look like. So if you want to subscribe to the activity, this is what the code looks like. The first thing you do is import the actual framework. So you import Core Motion. You declare your activity manager, right? So this is a CM Motion Activity Manager. And give it a name, right? I declared it as a property. Somewhere maybe inside view did load, you're going to call this CM Motion Activity Manager is activity available. What is this function right here?
It checks if the phone has an M7.
Yeah. Sorry, I'm talking way simpler than that. It's a class method, right? I'm calling this method on the class CM Motion Activity Manager. I don't have to have an instance to CM Motion Activity Manager to call this method, right? So it's a class method. If that method equals yes, which is true, it's just a type def, then I'm going to say, okay, self.motionActivityManager alloc init. Okay? It's instantiated. The next thing that I'm going to do is I actually want to sign up for updates, right? So what I'm going to do here is, okay, so maybe this is in some other block of code somewhere. I'm going to say, is activity available? If yes, start activity updates to queue. So I'm going to subscribe to this queue. So essentially, I'm going to run this on the main queue with all of the UI. And for the activity manager, that's pretty okay. You're only going to get an activity update when activity changes. Okay? That's going to happen once, not a whole lot, right? Maybe once every 5 seconds or something. Okay? So you can run that on the main queue. I'm not going to ding you for that. Okay? So essentially, I'm going to run this on the main queue. And this is the block that I'm going to define to handle my CM motion activity. Right? So what is this CM motion activity? It's an input variable. Okay? And then I'm going to do something with it inside this block. Otherwise, if stuff wasn't available, I can't start the activity manager. Okay? Whenever I'm done with that, I want to say I want to deregister my app. I don't want to have it send updates to my app because it will send updates to your app. Okay? If you don't tell it not to. Fair enough? So what's in an update, right? What's in this little function that happens right here? Start activity updates, a CM motion activity. What is that? So, like I said, it's updated when any part of that estimate changes. Anybody want to know what time it is? I have no idea what time it is.
47.
47? 3 minutes. Okay, so it updates when any part of the activity estimate changes. And you're going to get an update. And inside of this activity function, you're going to get access to all of these fields. Start date down to seconds. And whether the user was walking, 0 or 1, that's a field. Stationary, 0 or 1. Running. In a car, automotive, which is 0 or 1. Or unknown. It's also going to give you a confidence and how confident it is with the estimates that it gives you. And that's going to be low, medium, or high. Okay? So maybe you only want to do things when it's really, really confident that the user's inside of a car. Question?
You still have access to all the raw data if you want, correct?
Mm-hmm. And we'll use that. But essentially, this is not an activity that comes back as, oh, the activity is walking or the activity is automotive. It is a set of activities and whether or not those are active. This right here is not one hot. What do I mean by that? Well, you could be in a car and stopped at a stoplight. And stationary would be true and automotive would be true. Okay?
Did you say you don't also have biking?
Biking is not in here. Biking is implemented by the Moves app. Okay? They had an algorithm essentially that kind of did cycling and did it pretty well. They left it in. They're using the M7 coprocessor for everything else. Not only that, when users are sitting there, they're actually uploading motion activity with the Moves app. And every time you sit there and you say, oh, I was swimming or I was working out or something, I had my phone on me, you're giving them data that they are going to use to build a model to automatically detect when you're working out, swimming, all of that stuff, if you have your phone with you, right? They're crowdsourcing their machine learning. Okay? I think it's pretty neat. But it's also something that you guys could do from this class. Am I out of time? I am? Okay. We will stop there. And on Monday, I will pick back up and we'll do an example demo. If you have any questions on the audio manager stuff, let me know. I'll get back to you on the memory leak. Sorry, Wednesday. Yeah.